Okay, today we're going to look at Newton's second, but now it will be time-dependent forces. Remember the last video we did constant forces, or forces that are not dependent on anything, or time, velocity, position, or so. So we're expecting that our function now will be a function of t. Our force will be a function of t, right? So let me make an example of a mass of 2 kg, and then there's a force of which is changing with time for t newtons, obviously, and then I say that at block start from rest, let me say block start from rest at position x is equals to 0. Also know that v at 0 is equals to 0 because I set the ball start at rest. So I made up this problem so that it's easier for me to solve it. Okay, mx dot t is equals to ft. Remember, this is just Newton second of saying sum of all forces equals to mass times acceleration. Alright, this is technically acceleration, this is a force, this is a mass, so it's actually the same thing. So we know mass is 2, acceleration is changing as time changes because the force is also changing as time changes. From here I like to write 4 as 2 by 2 so that I can easily cancel all the 2's. And now I know that the acceleration is equal to 2t. Then I can integrate both sides. Now I can have what? This one will lose one dot to become x dot t. If I integrate here, it becomes 2 all over 2 plus c, right? And this is our velocity, but we know that velocity at time 0 was equals to 0. So if we plug in, we get 0 here, get 0 here. If we plug in 0, then we'll get c is equals to 0. So this will just disappear. And then if we do it all over again, integrating now, and just to dt, I don't know, I'm not using dt's throughout, and then I'll get the position, the dot will go away, as equals to this side I'll get t3 all over 3 plus c, and then this is our position, and that somewhere here was our acceleration. So we can use initial value theorem again, that we said it started at position 0 as position equals to 0 at time 0, position is equals to 0. So I can say 0 is equals to, if I plug in 0 here, c is equals to 0, then I can get rid of that. So that's how you solve Newton's second for time dependent forces, remembering that also force now depends on time. So if you integrate both sides, and then yeah, the math happens. Okay, now we're going to do velocity dependent force, aka linear drag. So you know, if I call it linear drag, so it's literally very associated with friction, right? I did talk about this on the previous video when I explained how velocity dependent forces work, so you please check that first video. Okay, so let's say force drag is equals to some constant and velocity. So now whatever force of drag that we get is a function of velocity. Like if you've been on a car, you say this is your car, and you take your hand out, right? You can feel air rushing on you, right? You know that whatever your hand does cause drag, and drag is a force that is a function of velocity. And you know that as a car go quicker, if that's the word, quicker, there will be more drag, and then if it goes low or maybe stationary, there won't be any drag. So I'm trying to give you an example where force is a function of velocity. Then let me say C is equals to 4, force is equals to 4 Newton. I'm trying to make a similar problem. Mass is still at 2 kg, right? So we know that F net is equals to MA, that is our Newton second. So F net now, the force is going to be 4 V. Alright, let me say V, 4V, right? Mass was what? Mass was 2 D let me say dV dt to make sense, because if a differential of V is acceleration, that's me writing acceleration in a more simpler way. I could have written this part as dx squared over dt, like that. Still the same thing, right? I'm just going to keep it V because everything here looks like it is in terms of V. Then my dV dt is equals to if I write this 2 as 2 by 2, then I can get privilege of just cancelling like that. And then now I have dV is equals to 2V, right? Now it looks like that. Now we're going to employ a scale of which I hope you have seen before, because we're trying to we can't integrate both sides here because we're trying to integrate in terms of t. We call it separating of variable, I think. Yeah, they call it separating of variable. So we can take this dt, take it to another side, taking it here. So it's going to be dt alone, and then this side I'll have dv all over 2v, right? Everything with v is on the other side and everything with t on the other side. That's why I call it separation of variable. Then I can get to integrate both sides as much as I always wanted to. And if I integrate here, I'll get let me take 2 outside, or let me just take 2 to the other side because it's simpler this side. And then I'll have ln v is equals to 2t, right? Remember, I'm trying to solve for v. Then I can put them as powers of e, both of them. And then this side I end up having 1. But remember here I got a c before. I mean this c is on top because I got a c before I put everything on e. Then e will cancel everything there. I'll be left with v, and this side I'll have e to t plus c, right? I can still employ the same principles of using initial value theorem. Remember now I'll have a constant here, but this constant, remember when they said in high school if the posts are the same at the exponent, this is the same as having e here multiplying and by c, and this guy alone, he is a constant. I could have just called him c because e power c, e to the power constant, that's a constant that we also don't know. So it's just convenient to just write this thing as a constant c, right? Because I already used c there, it would be wrong. Let me just use some constant a, right? I can still apply what we did there in the beginning by saying that it's no time or time initial, maybe this thing was moving at 10 meters per second, right? So I can just get to plug in everything here and set 10. Then if I plug in 0 here, this will become 1. Then I'll be left with a. So now I have a constant a. Then my v is equal to 10 e to t. That is my v after applying my initial value theorem. Now you were like, okay, now how can we move on from this? Then we'll have d position, let me say dx dt, of which that technical velocity is a. We already know it, 10 e to t. We're trying to get this guy now. Technically, we're just going to take multiply by dt this side and then integrate both sides. Here we integrate into d in terms of x, then we're going to get some position in terms of t. And if we integrate here, you know that what do you call this, exponential function, if you integrate them, they technically do not change. If I integrate here, that 2 is going to divide that 10. I'll have a 10 over 2e, and then this guy won't change, but I obviously have to get another constant called k, right? And then what can we do now? So this is it. You can still use that at position times 0. We were at position 0 and solve for k. So that's marked the end of our video. Please be on watch for other videos containing this course, applied math 1b, dynamics in this case. Thank you.